Greetings everyone, Ernest Heaviside here. Today's topic is trigonometry. This is extremely important and is widely used throughout all of higher level math. More importantly, it's a great chance to learn how to approach and solve problems. The problems are simple enough and highly intuitive and based on geometry. So a great foundation in math starts here. Now let's get into it. When working with triangles, there are many different shapes we can draw: obtuse, acute, and everything in between. However, it's most useful to start talking about right triangles. So this is a right triangle. You can see that this is a right angle here. And there are several different reasons for that. First of all, take a typical XY coordinate system. You can see that there is a right angle here. This is what we call orthogonal. It means that you can travel in one direction without traveling in the other direction. So you can imagine if my x-coordinate actually stretched this way, as I progressed along it, I would also be progressing up the y dimension. So this would no longer be orthogonal, in other words. So if I have a point, I can describe any point in my space with just two coordinates, the x and the y coordinate. These form a grid, and I can describe any point on this grid with just two coordinates, the x coordinate and the y coordinate. So you can imagine if I'm an ancient sailor and this is my chart, this would be my longitude and this would be my latitude. I can describe anywhere I am on the chart using just two coordinates, the longitude and the latitude. So on this coordinate system, I have an x coordinate and a y coordinate. And a line to the center would look like a right triangle. So if I wanted to know my distance from the center in terms of my coordinates, x and y, I would need to know something about right triangles. Second of all, this is a rectangle. This side is length A, this side is length B. The area is A times B. And this is actually how multiplication is defined. It's the area of a rectangle like this. So you can see that these are right angles here. And we can define any right triangle this way as the bisection of such a rectangle. So the area of this triangle, as you can see, the triangle on this side is the same, just flipped. And that's because these sides are the same length, and this is the same angle here. So this is the same triangle, just flipped. And so using this, we can assert that this rectangle is, the area of this rectangle is two of these triangles. So that means the area of any one of these triangles is half the area of the rectangle, or AB over 2 is the area of the triangle. So it's convenient that we can get the area of a right triangle very easily. So now that we know that right triangles are important, how do we get a relation between A, B, and C? It's surprising that many people actually don't know this, don't know the proof for this. If you don't know, I advise you to stop the video now and try to figure it out for yourself. As a hint, you want to be using geometry to your advantage. You want to be assembling this triangle in such a fashion that you can find a relationship between A, B, and C. Now, proceeding with the solution, we assemble our triangle into squares. These are the sides. And we are essentially taking advantage of the definition of multiplication, which is defined as the area of a rectangle, by assembling our triangle into squares. So you can see there's one big square along the outside, and another square made out of the length of C on the inside. So the area of this is the length of the sides multiplied together. So that's A plus B times A plus B. Another way to get the area is to add up the area of the internal shapes. So that's the area of this square, c squared, plus the area of each individual triangle, which is AB over 2, and there's 4 of them. So setting these equal to each other, we have a relation. Distributing out the left, we get this, and now canceling out the 2AB, we have our result. A squared plus B squared equals C squared, a formula that relates the sides of the triangle to the hypotenuse. Now, it's important to note that you could have discerned much about this solution without even doing anything. So first of all, you know that C relates directly to A and B, because you can imagine stretching B changes the length of C, and stretching A changes the length of C. So C is going to be a formula based on A and B. Also, you know that this has symmetry, right? So you can swap these sides and it wouldn't change anything. It would look exactly the same. And so you know that whatever formula you get in the end, you'll be able to swap A and B without changing anything in the formula. It'll calculate to the same result. So there will be symmetry. This type of reasoning process is very important when it comes to solving more mysterious problems in the future. It's instructional. We can apply the same reasoning process, and we are learning how to solve these problems in general. That's why it's important, if you're serious about this, that you take the time and effort to work through it yourself. Even if it takes you a very long time, you will learn a lot from the experience. Now, we know how to get a relationship between the sides of the triangle, but these angles here also have a relationship to the length of these sides. So can we get a relationship between the sides of the triangle and this angle here? So with respect to this angle here, this is the opposite side, this is the adjacent side, and this is the hypotenuse. So as theta changes, the ratio of these sides will change too. So we define the ratio of the sides in terms of theta. So first we have sine of theta, which is the ratio of the opposite side to the hypotenuse. Then we have cosine of theta, which is the ratio of the adjacent side to the hypotenuse. Then we have tangent of theta, which is the relation of the opposite side to the adjacent side. We don't know how to calculate anything about these yet, but we can get a good first impression at least. So theta is now the variable in a function. So we seek to widen the domain of theta as big as possible. So to that effect, we place our triangle on a coordinate axis, and theta is now free to go to negative degrees and degrees that surpass 360 degrees. So what if theta gets really small? What if it goes to 0? Well, you can see that this opposite side goes to 0, and the adjacent side goes to the same length as the hypotenuse. So we know that the sine of 0 is 0, and the cosine of 0 is 1. By the same effect, when theta goes to 90 degrees, you can see that the opposite side goes to the same length as the hypotenuse, and the adjacent side goes to 0. So we know that the sine of 90 degrees is going to be 1, and the cosine of 90 degrees is going to be 0. And so what if they're both equal? What if they're both the same? So we know that the length of this side will equal the length of this side. So we know that the sine is going to of 45 is going to equal the cosine of 45, which, by the Pythagorean theorem, will leave them both equal to 1 over root 2. Now, what if theta goes to negative degrees? Well, you can see that the opposite side goes to like a negative number, but the adjacent side is unchanged. So you know that the sine of the negative theta is going to be the negative sine of theta, while the cosine of a negative theta is going to be the same. So using this analysis, we can flesh out the bare bones of our function. And that's important for getting a general understanding of what our function looks like and how it will behave, which is actually very important, it turns out, in calculating these quantities later. So, although we can't reliably calculate the sine or cosine of a value yet, we can get some basic relationships between the functions. These are the basic trigonometric identities. There's a whole bunch of these, and I would encourage you to look them up and prove them for yourself. One important one is that tangent of theta is the sine of theta divided by the cosine of theta. And this makes sense, because opposite over hypotenuse divided by adjacent over hypotenuse is opposite over adjacent. Another important one is that sine squared of theta plus cosine squared of theta is 1. This comes from the Pythagorean theorem. The opposite squared plus the adjacent squared is the hypotenuse squared. Divide both sides by the hypotenuse squared, and you get sine squared plus cosine squared is 1. Now that we have some relations that describe a right triangle, can we get some relations that describe any triangle? And yes, we can. This is the law of sines. So you see we have a triangle here. It's not a right triangle, and we seek to find a relationship between these angles and these sides. Here's what it looks like. So I'd encourage you to pause the video and attempt to work this out for yourself. Attempt to prove it for yourself. Moving on. Here is how it's done. You divide this triangle into two right triangles and relate them through the common height m. So the sine of beta is m over a, the sine of alpha is m over b. And using algebra, it's trivial to prove the law of sines. Now, a more difficult relation, but more useful too. This is the law of cosines. Once again, this is not a right triangle. It has an angle omega here instead of a right angle. Now we're going to try to prove the equivalent of the Pythagorean theorem for an arbitrary triangle. So if any brave adventurers want to try to do that without even knowing the formula, now is your chance. Alright, here is the formula. This is what it looks like. So I would strongly encourage you to pause the video and attempt to prove this for yourself. Otherwise, we're moving on. Here is how it's done. Once again, you divide it into two right triangles. And now, we're going to try to find a relation between these two triangles using the Pythagorean theorem. So on the left, we have b squared minus p squared equals m squared. On the right, we have c squared minus q squared equals m squared. And now we have a relation through m. And we're going to try to do algebra on this. Here, let's follow the steps. So we're bringing b over here and q over here. Now we're going to factor this side over here. Now we're going to substitute in a for p plus q, that makes sense, and p for b cosine omega, because that's what p is over here. Here we go. And a little bit more algebra, and we have the law of cosines. It's important to notice that the law of cosines is a more general relation than the Pythagorean theorem. Notice that if this angle omega were to go to a right angle, this would turn into the Pythagorean theorem, because the cosine of a right angle is 0. I would be remiss if I didn't talk about radians. So one consequence of the law of sines is that if you scale up any triangle and keep all the angles the same, the sides have the same proportion. So the sides will scale up by exactly the same amount. So for example, if you multiply one side by gamma, a constant, then all the other sides will be multiplied by the same constant, gamma, including, most importantly, this diagonal side, c. As a consequence of this, if you have 2 points here, P1 and P2, and they have a delta in each of the dimensions, delta x and delta y, if those deltas multiply or scale, then this delta r will multiply by exactly the same amount, the same proportion. So as a consequence of that, because any shape is made up of a collection of points, if you scale any shape, then the perimeter scales by exactly the same amount. So in other words, if you multiply the shape by 2, if you increase the size by 2, then the perimeter doubles. If you decrease the size by half, then the perimeter is cut in half. And that is true for any shape, including, most importantly, a circle. So a circle, the circumference scales with the radius. It's directly proportional to the radius. That means that the circumference is a constant times the radius. That's what that means. So we call this constant 2 pi. Why 2? Well, because in the past they used diameter, pi times diameter, and that's because diameter is probably much easier to measure. So let's say we have a circle with a circumference c, and we want to measure the length of a proportion of this circumference, subtended by the angle theta. So how do we get s? Well, s will be the same ratio with c as theta is with the total number of degrees in the circle. So let's say we haven't decided on a measuring system, and the total number of degrees in the circle is d. I mean, normally it's 360 degrees, but right now we're just going to say it's d. So we assert that s over c, the proportion between this arc and the total arc, is the same as the proportion of the theta to the total number of degrees in the circle, d. So now solving for s and plugging this in for c, 2 pi r, we get this formula, which is very uncomfortable. So we choose a measuring system called radians, and that asserts that d, the number of degrees in the circle, is 2 pi. So that's very nice. If you have 2 pi on the bottom here, it cancels with the 2 pi on the top, and then you have this nice formula, s equals theta r. So in the system of radians, calculating the arc length subtended by an angle is very easy. It's just theta times r. So typically most trig functions, sine, cosine, tangent, are in radians. The most convenient measuring system to use with regard to circles is radians. Now that we know a little something about radians, let's put our knowledge to the test. Try and find the sum of the internal angles of a triangle in terms of radians. How will you approach this problem? How will you figure it out? Pause the video if you want to work it out yourself. Okay, here's how I would approach this problem. You're walking along this base here, pointed forward. You reach the end and then turn on your foot. You turn T1 degrees. Now you're pointed this way, walking this way. Then you turn T2 degrees, and then T3 degrees. Now you've got a full 2 pi radians in a circle. These outside angles here are pi. They're half a circle. Now, these internal angles here will be a full circle minus the outside. So it's going to be 2 pi minus pi plus T1. And same for the next one. And same for the next one. You can sum these all up, and you get the sum of the internal angles equals 3 pi minus T1 plus T2 plus T3, which is 2 pi. So the sum of the internal angles of a triangle is pi. Thanks for watching. I suggest you follow up, do some problems, and remember, a strong foundation is how you'll get good at this. So don't jerk the fundamentals. These are the fundamentals. So practice. Good luck.